Okay, welcome. This is Dr. Morton, and I'm just presenting the lecture that would have been done on Friday. So hopefully you've gotten a chance to look at this over the weekend before Tuesday. And then Tuesday I will do a live lecture on Zoom again. I will record it and I'll post it along with this one on Blackboard. So let me, I'll shrink myself down here and see if I can do that a little bit more. And I'll tuck myself in here. All right, this is the syllabus, and so here we are on the 20th, well, actually the 21st, and we're going to do, you need to do the prerequisite test. That would be really helpful, and we'll also, it comes in two sections. I think I showed it to you on Tuesday. One section is has to do with C language, and the other section is more like logic design and basic theory stuff. So just take both of the tests, and that gives me a score for each of the sort of prerequisite things. Makes it easier to do the A-bet analysis that we have to do. Okay, so enough of this. So here's a picture of the new board we're going to use this semester. You can see it has the ATmega processor here, a 32-bit low-profile quad flat pack. And here it has the 20-pin PIC16F1829, which is an SOIC package. The spacing on the pins here is a little more generous than it is here, and so this one's a little trickier to. We kind of have to be really careful when we stencil on the solder paste so we don't get too much on these pads. And actually, the students did a really great job on that. We only had one or two with little bridges on these pins that I had to fix afterwards. And when we ran these, when I ran them myself the first day or so, I made maybe 16 all total, kind of getting ready. I had quite a few of them with multiple bridges between these pins with solder because we had used too much paste. So there was one mistake on the schematic, and we left off this cap, so we have to put a through-hole cap into this prototype area. This is just a little area for doing projects. It's not otherwise for any other purpose. And then we wired it, and you'll see on the back of the board we ran wires. I took a picture of that too. We went a wire. This is the back of the board. The cap pins come through here. One goes to the reset pin on the ISP header, and the other one connects to this pin right here, the second pin in on the UART to USB connector dongle, if you will. And this pin is the DTR pin. It's one of the control pins in the UART interface. And this pin has to have this cap on it to shorten the pulse so that if we want to use this with the Arduino IDE, we can. And if you don't put this on there, it won't work with the Arduino IDE. Okay, so that's that. And when you solder these things on, we'll solder on the bottom of the board. So all the surface mount stuff is soldered on the top of the board here. But the through-hole stuff goes through these holes, but it's soldered on the bottom. So don't solder on the top. Solder on the bottom of the board for the through-hole stuff. Okay, so we're not going to populate all this initially. We'll wait till we get a little further in the semester after we've done some labs with the PIC. Then maybe the last couple of labs I'm going to rewrite them, and we'll do them with the PIC and the ATmega 328 PB. This chip is very, very similar to the standard Arduino Uno, but the Arduino Uno uses the ATmega 328P, and this is the ATmega 328PB. It has more memory. It has some features that the P chip doesn't have, and it's a little bit of a misfit for the Arduino IDE. So it takes a little. You have to add some special files to get it to work, but it does work okay. So that's the good news. All right. So we're going to focus on this part of the board initially. And the only things we're going to have to solder on, you're going to have to solder on a little 3-pin male header here that we'll put a jumper on. This jumper will select whether we pull 3 volts off of this USB header, or whether we pull 3 volts. So 5 volts or 3 volts. And then if we do, we'll also solder on this little plug here. And if you plug in, and we'll give you a battery connector. If you connect your battery, this voltage regulator will deliver 3 volts to both chips, but to this one as well. Now the 3 volts may not work with the ATmega. It should work with the ATmega 328, but it may not light the LED. So I don't know. Anyway, long story short, we'll probably not use this a whole lot. We'll mostly power the board by plugging in our adapter board here, and then plugging that into a USB plug. And then that will provide 5 volts and also 3.3, but we'll normally put the jumper in the 5 volt position. But if you're doing a project that needs 3 volts, then you can put it in a 3 volt position and run it there. Okay, we'll solder on this. So we'll solder on this 3-pin header, and those pins are male. They don't. Here we'll solder on this 6-pin female header. We'll solder on these 2 little push buttons. We'll solder on these 2 double row female 10-pin headers, one here and one there. We'll solder on this right angle 6-pin male header, and that's where we'll plug in the snaps to program this chip. The snap, we won't use it to program this chip. This chip will program through the bootloader and through this USB to UART dongle. We can plug the dongle in here if we want to use it with the PIC, but the only purpose here is for the PIC to write to a terminal window through that dongle. If we plug the dongle in here, then we can plug it into the Arduino IDE, and the Arduino IDE can program the Atmel, the ATmega chip. Okay, and then finally we'll put on this 5-pin female header here, which is our little analog header. And I have a little analog board which we'll loan you for the course, and you can, for some of the labs, we'll plug that analog board in here, and that'll work great. So we'll have this header, this 5-pin female, 6-pin right angle male, 2 by 10-pin female headers, 2 push buttons, 1 6-pin female header, 1 3-pin male header, and our 2.1 millimeter jack, so we can plug in the battery, and then you can solder the plug onto the battery snap. And so I'll probably give you all those parts. So that would be the battery snap, the plug, the jack, the 3-pin header. So that's let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there'll be 11 parts for you to solder on. Shouldn't take you but 20 minutes at the most, probably, or half an hour if you're really taking your time. But you do have to be careful. If you're not careful, then what happens? You get solder smeared all over the parts on the bottom, and you short pins out, or you don't have them really connected well. But I will do a solder demo on Tuesday to show you sort of some good solder technique. You're welcome to buy a soldering gun if you want, but we have one plenty to loan you at school to use in the classroom. Okay. Some of the features of this board: there are 4 touch pads. The letters U, T, S, and A can be used as touch pads. Obviously, you have to program this. They're not automatically touch pads. There's an RGB LED here, so there are 3 different colors. It's actually orange, blue, and green. The orange looks fairly red, so you can think of it as RGB. But actually, when I ordered it, it said it was an RGB LED, but it turned out it was an orange, blue, green. And I guess I did that so it makes a better white. The white looks really good, and I guess the orange makes the white look better. I don't know. I was a little shocked when I finally realized that it really wasn't an RGB, it was really an OGB. And then we have a lot of, these are the current limiting resistors for the LED. Here's a little cap to just help power it for when it blinks and stuff. And then we have some caps to despike this chip, and then we have some for our push buttons and for our reset button. So those are the parts on this part of the board, And then up here we have some more parts for the ATmega, and then we have the little voltage regulator and some caps that go with that, a whole bunch of caps actually, and a little diode so that if you plug the battery in wrong, it'll block, it'll keep you from screwing up the board. Okay. So that's that. Okay. So the rest of this document, which I'll post to Blackboard. I don't think it's on Blackboard now. I give you. We talk about, here are the pins that are connected to the PIC UART to USB interface. We're going to use what's called the CP2102 header. Here's what the assembled board looks like. Again, this is the PIC. You can see the little plug-in here, and then here's the little CP2102 dongle that takes a micro USB plug, and here are the two push buttons in place, and so forth. So we're only going to have to do the parts down here plus this plug up here. We will need to do the 3-pin male header that has to have a jumper on it for the chips to be powered. Okay, so so these are the pins that are connected, and I'll some of this is maybe getting the cart ahead of the horse because we really haven't even talked about this chip. But so this document though tells you how everything's connected. Tells you how the PIC USB to UART header is hooked up to the PIC, how the AT UART USB header is hooked up to the ATmega 328, how the PIC analog header is hooked up, how the AT analog header number 1 is hooked up, and then also number 2 and number 3. There are 3 different analog headers on the AT. And then the touch pads connect to these pins. The push button connects to this pin. The header for the snap, the programming header, connects to these. The snap programming header connects to these 6 pins. The 6th pin is not used on that header. Just 5 pins are used. And then this 6-pin ISP header for this is when you use the ATmega with something like Atmel Studio or now Microchip Studio. You can get a little programmer that will plug into here. But we'll use it with the Arduino Studio that uses the bootloader, and it just connects through this this UART to USB, the CP2102 dongle that connects them. And all it does is translate the UART information into USB format. Okay, and then the battery hookup. We'll talk about that. If you leave your battery connected, it will drain it. So don't leave it plugged in. There's not an on-off switch on it. So just unplug the battery if you're gonna if you're not going to be using the board. Otherwise, overnight it'll drain the battery to 0. Here are the pins that are connected to the RGB LED. Here are the pins that we use for I2C. This is the way we've connected the PIC and the Atmel together. There are two pins are used for 2 wires are used for the I2C interface, and so that takes 2 pins. 2 pins on the PIC, 2 pins on the ATmega, and they're connected together. They do have roughly 4K pull-ups on them. I think they're 3.9 or something actually. And then we did put an OLED header on it. This OLED header, I think I showed you it working the other day, but maybe I'll show that here in a second. But anyway, it turns out this one was another little mistake. Some of the OLED devices have slightly different pin arrangement, and anyway, we have 2 I2C headers on the board, and neither one is in the correct format to directly plug the OLED little screen into it. So we have to use DuPont wires and hook it up so we can get them in the correct order. So that was a little bit of a ding up, and we'll fix that on the next revision. And then this is the we have some pins that can be pulse width modified on the PIC. We put them in here. There's some also on the Atmel, but I didn't include those yet. All 20 pins are brought out on those 2x10 pin headers on the PIC chip, which makes it easy to find your pin. On the ATmega, the pins are a little more disorganized. If you look, you can see so PC3, PD2, PD3, PD4 up here on this 4-pin header, and this 6-pin header has PB2, PB1, PB0, PD7, PD6, PD5, and then some of the other pins come out on these headers. This is mislabeled. It turned out we put the same labels that we had here. We didn't mean to do that, so that's the third mistake. And I think there really are only 3 mistakes on it. Left off the cap, screwed up. Well, and then these 2 things are wrong. They're just hanging out here for no reason. We screwed up this, and then we screwed up the order on this for this OLED display. We didn't get these in the right order. They're the right things, but they're just not in the right order. So we can't just plug it in like we can on these. All right. Well, anyway, and then this is the other I2C header, which also we don't have to populate that. We can pull the same thing off on RB6 and RB4 here on these 2x10 pin headers. So anyway, all right, moving along. Yeah, and this shows the OLED header, and these are the pins. But it turns out they're actually laid out. Ground, power, SCL, SDA. All right. Well, anyway, and then yeah. So, and then the LEDs that are on the board. There's an LED that's the standard LED that goes with the Arduino Uno, and I think it's connected to RB5 here. And then there's a power LED that's always on here. So whenever the board's powered, this should be on. If the board is not powered, it won't be on. So if this isn't on, your board's not powered. Even if you have power plugged in up here, you may not have the jumper in the correct place. You can have your dongle here and plugged into the USB port, but if you don't have this jumper on, there won't be any power and this light will be off. And then finally, the RGB LED is right here. Okay. Yeah, and then when we get ready to use the Arduino Uno, then we'll give everybody one of these 100 nanofarad caps, and we'll have you solder these little wires on the bottom side. We'll give you the wires too, and then that'll enable it to work with the Arduino IDE LED, and we'll have you solder on all the headers that relate to the ATmega chip. Okay. Okay, now I want to talk about, I want to go through some slides. So, yes, dear algebra, please stop asking us to find your x. She's never coming back, and don't ask us why. A little mathematical humor there. All right, so we're going to kind of, so some of this, I haven't decided how much we need to charge. It'll probably be $12. It might be 15. I'm still trying to figure out what the snaps are going to cost me. So we'll see. We don't have a text for this course. We just have the data sheet. There's a data sheet for the PIC. There's a data sheet for the ATmega 328 PB. I have been studying the data sheet for the ATmega 328 PB. I've mostly been focused on the things called fuses and lock bits. But as time goes on, I'm going to get up to speed on the various peripherals and all sorts of stuff, and I will present that to you. At this point, I'm still sort of in the learning phase with this chip as well. I've used it with the Arduino Uno, but I haven't delved into the actual hardware on the chip. The nice thing about the Arduino world, all this software is already done for you, and you don't even have to think. You just click, 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 and these professionally written programs start running. And you can download them, and there's a program for just about anything you want to interface it to, and there's usually a good YouTube video or 2 or 3 or 4 or 20, maybe 10 or even 20 different YouTube videos showing you how to do it. So this will be kind of fun, but it'll be a little tricky for ours because ours isn't laid out with the actual Arduino footprint. We have our pins kind of scattered around, and that wasn't accidental. It turned out if we had put the Arduino footprint up there, we would have had trouble fitting it into the 10 centimeter by 10 centimeter size constraint that we had. All right. So I like I said, I am going to show you. I'll do a little solder demo on Tuesday. I don't think I'm going to do it today just because in interest of time. But we will have solder equipment available in the lab, and also I'll try and set some up over in the atrium. And like I said, I don't think it'll take you more than 20 minutes to solder on what I say, the 14 parts or something. Usually the Eta Kappa Nu does a solder demo for our students, and I don't know if they'll do that. Nobody's contacted me yet, so I haven't heard. COVID has definitely created some problems with this. The IEEE parts bin sometimes is involved in selling these things. I don't know if we'll have them do it this time. It's a little, yeah. Sometimes, usually what I do is we take care of the initial selling the initial parts to students, and then we take supplies to the parts bin, and then they finish up. Sometimes they'll finish up selling to the students, or maybe not. I don't know. And then we have the 3 parts that we're just gonna loan you and we want to get back, and that is the CP2102 dongle, the cable that goes with that, and the analog board, and then a 2-line by 16 LCD display. So those are things that we'll pass out for you to use for the semester, but that we want you to give us back, or we may just have them in lab and have you use them during the lab, because I think I came up pretty short on parts at the end of the semester, and so I don't know. I'm not sure what percentage I got back, but it was not anywhere close to 100%. So maybe we'll just have them in lab, because then I have to go out and buy more, and they're kind of pricey. Not bad, but $4, $4.50, $5 for the 2-line by 16 LCD display. The little dongles cost me maybe $2.50, $3. The analog boards are mostly they're not expensive, but I have to solder them together, and it takes me a good long time to solder. 20 of them takes me about 2 hours to solder together. So it's nice if I get them back. It's helpful if you have some DuPont wires, but we do have some we'll give you. So here are the things you'll get to use for the semester. If you want to take them home, I'll probably let you do that, but mostly I'll have them available to be used in lab. And that's the CR2102 UART to TTL to USB dongle, a 2-line by 16 LCD display with an I2C adapter board, and a custom analog board with temp photoresistor in the pot. And we also have the cable to go with the dongle here, USB micro cable. Okay, when you get ready to do your project, I have lots and lots of parts that I will either loan you. Well, usually I like to loan you. If for some reason you want to buy them, I'll let you give me some money, but I prefer not to do that. But in any event, I have lots and lots of different things to interface. RFID readers, GPS receivers, GMS receivers, so you can talk to the cell network, but you do have to have an account for that. You have to have a data account, but that's kind of cool. Then your Viva board can talk practically anywhere in the country to the internet, and so forth. Well, not anywhere. It has to be within a cell tower range. And a whole bunch of other parts. Temperature sensors. Well, we have one on this analog board. Accelerometers, humidity sensors, soil moisture sensors, servos, stepper motors, a lot of stuff. Okay, so the first week is really just getting your board constructed. Since we kind of skipped this week because of the weather and whatnot, and also we didn't have them all done, although we could have passed out a bunch of them, but only 60 some odd. So we'll try and get most of the boards passed out to the 90 students in this course next week on Friday. So I'd like everybody, if you can, to plan on coming to UTSA to the lab in the engineering building, second floor. It's 020422, and have $12 to $15, and we'll take your money and give you the Viva board and the extra parts to solder on. We'll give you the first set of parts to solder on for the PIC, and then we'll give you hopefully the snap programmer and a micro USB cable for the snap. All right, so that's hopefully what we'll have next Friday. I do have a fair number of snaps now, but I'm hoping to get the rest of them soon. So I may not have enough for everybody on Friday. We'll see, but hopefully we'll be close. All right. We're going to talk about how a microprocessor works, the programmer's model, how the memory is organized, how the instruction set works. The instruction set is the assembly language instruction set. And we're going to learn that. We're going to use that for the first several labs. You're going to take a test on assembly language programming. And mostly I want you to get a good taste of basic assembly language programming. You won't become an expert in it for the most part. I guess some will take an interest and be pretty good. But I want you to see how the chip works. And in order to learn the instruction set, you have to learn how a chip works. In order to learn how a chip works, you have to understand the instruction set. So since they kind of go hand in hand, and as engineers, computer engineers and electrical engineers, you need to know this, that's what we're going to do. And then we'll make a transition and use C for the remainder of the labs. We'll look at the instruction set for the ATmega 328, but we'll mostly I think we won't program it in assembly. We'll only program it in C. We'll look at besides the actual CPU part of the chip, we'll look at all the other modules that are on the silicon die as well, which includes a whole bunch of things, just a bunch of stuff. A to D converters, D to A converters, PWM things, capture things, compare things, timers, multiple different timers, comparators, and then a whole bunch of crazy things. Modulators, I don't know, I'm leaving out some stuff. But there's quite a few different modules. And then, of course, there are just the general GPIO chips that you can use, general purpose input-output, GPIO. And those GPIO chips can simulate practically any protocol. Oh, I2C, SPI, yeah, a good number of different peripheral modules. And I haven't named them all. There are quite a few more. We're going to look at the integrated development environment and the tools that it provides to support your development. We'll also look at, we'll probably look at Atmel Studio briefly, and we'll definitely look at the Arduino IDE. And then we'll do some work on programming. We'll talk about programming assembly, of course, you'll learn that, and then we'll also do some review of C, C++. For the most part, this chip will be programmed in C, but there are some C++ features you can use, I think. But it's not, even the C is not a fully ANSI standard C because there are some hardware limitations to the chip. And the biggest one is it doesn't use it doesn't have a stack pointer that can be pointed towards memory wherever you want. It has a hardware stack that's only 16 levels, and so that limits it to nesting things no more than 16 level deep. Function calls in assembly subroutines, and we always have to throw in one more level for a possible interrupt. We will learn about interrupts as well. Okay, so we need what I really want you to do is the transition from looking at microprocessors as kind of an unknown black box to where you really have a pretty good idea of what's going on under the hood. And if you understand how one chip works, yes, there are differences between chips. Quite a few differences, but they all generally have the same basic features. And so for that reason, then, if you learn one, you really have great insight into every other microprocessor. None of them are so different that you wouldn't have a basic idea. You need to understand how the instructions actually get executed and how the chip does stuff. One of the things that's quite shocking is when you see that you can actually reach into the chip and change a bit in any memory location or any file register you want, any special function register. And when you do that, if that bit happens to be connected to a pin in one of the ports that's driving an LED, you'll turn the LED on and off. Or if it's doing something else like a solid state relay, you can turn a motor on and off with that. You'll see that we have this really nice integrated development environment that gives us all sorts of debug and debug help and tools to help us get code done, and we'll hopefully work on learning some of that. I know most students don't really dig into the debug tools, but they can be really helpful when you're trying to debug a program. So it's really good if you do work on that. We're going to help you understand how the high-level language of C or other high-level languages get translated into an assembly language program, and that assembly language program is then what's actually loaded into the chip and run. So it's really good to know kind of how that works, because that is the reality. And it's also good to know how that is, when it executes, how it's actually affecting bits in various functional modules and various general input-output ports. On this chip, there's no Windows. There's no operating system. Now, there are micros that are complex enough to have what's called an RTOS, a real-time operating system. Windows is not an RTOS. Windows is not real-time. Windows is pseudo-time. You can't be absolutely certain and guaranteed that Windows is going to get around and service your application at exactly the same time every time. That may not happen. But in a micro, when we're like sampling data and doing things like that, we want it to be real-time because we want to have predictable latency on things like interrupts and sampling times, and otherwise you get your samples are modulated with the jitter in your system, and we don't want that. So there's lots of constraints on microprocessors that are not necessarily on microcomputers per se. And on our chip, though, it's not really neither one of these chips is really complicated enough to warrant needing to use a real-time operating system. So there will be no operating system. The only code, except for a small loader, a bootloader in the case of the ATmega, and a little C loader in the case of the PIC, and also the ATmega for that matter, that actually gets everything loaded up and then transfers control to the starting point in the program. Other than that little bit of code, everything else is just what you've written. That's the only thing that's in the machine. And when you write an assembly language program, it is absolutely that. Only the instructions you wrote are the only ones that wind up in the machine. So you know exactly what the machine has, what it's doing, and if it has a problem, it's a little easier to sort it out. Debugging is always hard, but when you have to debug something that might be a problem in the operating system, or maybe your code, or you're really not sure, then that can make things even worse. All right. So I want you to finish this course with the confidence that if you were given a microprocessor and you were told by your boss to figure out how it works, learn your integrated development system, figure out how to get it running some code, that you would have the confidence to wade into that and be successful. Okay. So we're going to go over the programmer's model. Let's see if we have time. We may run out of time today. Well, we're doing okay. Yeah, so we're at 33 minutes. Okay. So then on the PIC, we're going to learn a lot about the PIC. Before COVID, we also used to get out KL25Zs and have everybody do a couple of labs with them. I probably won't do that this semester. We'll see. For one thing, I can't buy any KL25Zs. They're just not available, so that's a problem. And then the labs we have for the PIC and introducing the ATmega 328 along with that, they're going to be, I think, really useful and more helpful than getting distracted with the KL25Z. But the reason for this was the KL25Z it's a entry level, but it's a 32-bit processor, It's an ARM core. It's an ARM M0 Plus core, and it's a very complicated chip. Significantly more powerful than the PIC, but not orders of magnitude more powerful. But the PIC's an 8-bit chip. The KO25Z is a 32-bit chip, and it has a lot more. It has a lot more program memory, and it has a fair amount. It has a good bit more random access memory, but it doesn't have. None of these chips typically have that much random access memory. But the KO25Z, if we do this, which we probably won't, we would only program it in C. All right, we'll learn about how you have to care and feed the hardware so that a chip works, so it's set up correctly. We'll at least talk about that at some length. We'll also talk about how you interface it to other devices. You have to think about voltage levels and speed and all sorts of stuff, and how many pins it takes, and if you're interfacing several things, do you have enough pins to interface all the things, or are you going to have problems? And then we're definitely going to learn how to use the on-chip functional modules, how to configure them, and how to actually get them to work for you, and maybe some advanced topics. All right. So microprocessors have definitely evolved. We want to talk about the basic architectures, how an instruction is actually crunched, how the peripheral functions work, and just kind of some of the guidelines for embedded design. All right. So this is a little bit of a busy slide, but early machines were purely mechanical things. And then when we finally actually had working computers, they were actually very large rooms full of vacuum tubes, lots of power. I worked on an IBM 1620. It was one of two computers in my town of just under 100,000 people. Back in, I guess in 1963 is when I did my first programming. I had basically spent the whole summer hanging out in the computer center at our local college and learned how to program in Fortran and assembly language, IBM 1620 assembly. The power company, when they installed the computer, the power company had to install a special power drop, 3-phase 440, and the computer was in a room all by itself with lots of air conditioning because of the heat generated by the tubes, and it required a fair amount of maintenance. It had core memory. I'll show you a picture of that in a minute. And the IBM 1620 rapidly, IBM made much bigger computers, the 701, the 360. From about 53 to 63, there was just a huge evolution of these machines, and with tape decks. But there wasn't, the computer I worked on had no disk drive. It had 2K of random access memory, which was core memory, and that was it. It had no EEPROM. It had no no disks, no volatile storage other than the 2K, and no permanent storage other than stacks of punch cards. And it had a high-speed punch card reader-writer, and when you wanted to write your program, you would type it in on a key punch machine, one card at a time, one line at a time, and then you'd feed your cards in, and then it would actually compile the program, and it would punch out an object deck, and then when you're ready to run your program, you would take the object deck and load it in with a bootloader, with two punch cards that were actually a bootloader, and that bootloader would then load up the rest of your program, and it would run. Remember, maximum memory was 2K, so your program couldn't take up all 2K. Well, I guess it could take up 2K, but it couldn't take up any more than that. Now, there were some ways you could overlay and do crazy things, but slowly these machines got bigger and bigger and more powerful, and eventually we got to the point where we had a big machine on campus, and then we would have terminals all over campus where you could type your program in on the terminal, like a regular typewriter, or regular, I don't know, like a little mini computer, and that's in fact how mini computers really came into being. They they transitioned from dumb terminals to smart terminals to standalone mini computers. Anyway, so at this point, we have our break off where we started putting the whole where things went solid state, where instead of vacuum, and some of that was happening back here, but instead of vacuum tubes and core, we actually had integrated circuits. And as the integrated circuits got bigger and bigger, one of the first computers on a chip was the Intel 4004. It was a 4-bit computer. Was really limited, had to buffer everything, but it was the first computer on a chip. Truly amazing for its day. And then they moved up to 8 bits, and that was the 8008. And it required lots of support chips to make it work. But then we had the 8080, which was a little more robust in itself. And then from the 8080, we went to the 186, 286, 8386, 8486, or that was actually the Pentium as well. And then from that, we went to the rest of the line of Intel chips. And, of course, AMD came on board as well, started making chips to run the same instruction set. So this instruction set's been around since the 8008, basically, or for sure the 8080. And that's why it's pretty outdated. So the microcomputers then kind of went one way into PCs, and then obviously more fancy into mainframes. But a lot of these single chips went the other direction and became standalone microcomputers or microprocessors. And that's where embedded design really came. And whereas mainframes evolved to supercomputers, cloud computing, quantum computing, and we're still working on this. All right. So we're going to build the new board. Initially, we'll just put the supporting chips for the PIC, and then later on we'll come back and do it for the ATmega. We're going to do 10 labs. At least 1 or 2, or maybe more, we'll use both microprocessors. I think there's 8 homework sets. We'll do 2 tests, 2 midterms, and a practicum. And the practicum will be in person, in the classroom. Everybody brings their laptop and their Viva board, and then we'll give you a little sheet. You can work in teams of by yourself or with 1 or 2 partners, so a team of 1, 2, or 3. And every team will get a different assignment. You can pick your team and do whatever you want. And every team will get a different assignment, but they'll be very similar. And if you can write the code in the hour and 15 minutes to execute your assignment, to do your assignment, then you get a 100%. If you miss it by a little bit, then we'll take a few points off. If you really bomb it, we probably won't kill you any worse than a 60 or 70. Okay. So let's see. I think we did this. We talked about the history a little bit. I'm not gonna. One thing I do want to show you is one of my friends has one of these cards, and if you look underneath this plastic cover here, which says warranty void if this cover is removed, here's what it looks like. I wish I'd put a hand in there, but this card's about 6 inches wide, and so you can see when you look in there, these things are really tiny. But if you magnify them, this is what they look like. And you can see they're little bitty ferrite rings here, and they each have 1, 2, 3, 4 wires going through them. So 4 wires go through each one, and some of the wires are used to read and write and then sense and rewrite, and so there's X drivers, Y drivers, sense, and inhibit lines is what it boils down to. And you could magnetize this little bead, one of either counterclockwise or clockwise. and one would be a 0 and one would be a 1, and the other way would be a 1. And so that's how the memories work. And these are pretty fast, not nearly as fast as solid state memory is, though, of course. Here's a little more of a blown up picture. These are traces on the printed circuit board, and here are the little ferrite beads. This gives you a much better sense of how small they are. They used to have basically almost conscripted laborers in Indonesia that would thread these by hand. I have no idea how they could do it. And then they'd bring the wires out and solder them on here and solder them on there. And if everything's hooked up correctly, these work pretty well. Here's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 ferrite cores in each row, and they're 8 rows, right? 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits is a byte. So this is 8 bytes of memory, core memory. And here, this scan disk has 8 billion bytes. 8 bytes, 8 billion bytes. And it's considerably smaller. So that gives you an idea of what's happened over time. Here's some of the other computers. I worked on this one. This is an Apple II. Had 2 floppy drives. I had a Japanese knockoff, actually, called the Japple. Here's the PET computer. When I spent some time in a lab in England, I played Space Invaders on this a lot. Here's kind of the original TRS-80. This is it used literally a cassette tape recorder was its non-volatile hard drive, if you will. Not hardly random access though, because you had to play the tape beginning to end, and it just used sounds. Later on, they added floppies. They added these same kind of floppies to this system up here. We called it was labeled a TRS-80. We called it a Trash 80. The keyboard wasn't debounced, so when the keyboards were brand new, they worked pretty well. As they got older, they were really crap. And additional features came out to make them a little better. Like I said, the floppy drives came out shortly after this. But, in fact, I guess they're right there. There's some floppy drives right there, I guess. Well, I can't tell if it is. Maybe it's just a card. But anyway, the floppy drives look the same as this. These just happen to be Apple ones. Here's an early IBM computer. This is really the first really professional one. Up till here, these were kind of toy machines, really. You could do some real work with them, but it looked a little silly because they were pretty robust. I mean, the Apple II worked pretty well, but the Trash 80 didn't. It was pretty unpredictable. The PET was okay. It worked pretty well too. All right. So the 1960 Apollo guidance computer was nothing compared to today's simple chips, and but what it did, it caused a quad NAND gate integrated circuit to drop from about $1,000 per chip to $3. So that was quite a jump. The first computer in the automotive world was in the 1978 Cadillac Seville, and it basically was called the Trip computer, but it was basically just a little dashboard bauble that displayed mileage and some other trivial things. This day, that kind of microprocessor muscle could barely adjust your mirrors. It was a 6802. I did my PhD thesis on a 6502. Anyway, yeah, pretty amazing. All right. Okay. So I want you to know the difference between a microcomputer and a microprocessor. So here's an Intel Core i7. That's a microcomputer. It requires a big motherboard with memory slots, graphic stuff, lots of power, coolers, and all this other peripheral stuff. Chips to drive the PCI bus, interface lines for the memory, and This chip right here is a dedicated application-specific integrated circuit that basically basically makes the motherboard work essentially, and also on here there's USB plugs and all sorts of stuff, and you may plug in a separate card, or you can use the onboard graphics generator to look at it, pop it out in VGA or maybe HDMI or whatever. So this chip by itself, it may have some cache on it. It does have cache on it, but it doesn't have a lot of memory. It doesn't have a non-volatile storage. So when this chip powers down, everything on it's gone. The non-volatile storage is going to be in some EPROMs on this motherboard, and then also on the disk drive. The memory on these boards is dynamic memory, requires continual refreshing to make it work, but it's a lot more dense than static RAM. Here's a big microprocessor with a gob of pins, probably 80 pins, and 20 to a side. And this processor has built-in capabilities for all sorts of functionality, A to D conversion and D to A conversion and PWM and all sorts of stuff, I2C and SPI, and it just goes on and on. And you can pop one of these in a robot, and with a few extra chips, you can run the wheels with some PWM stuff or whatever. You can communicate with somebody, another program, say running sensors to see where the robot is and how it's doing, or maybe you're going to use it with a remote controller. And then inside this robot, it can have actuators, it can have all sorts of stuff, all controlled by this chip, without having to add a lot of extra other chips. So there are a lot of big families of chips. Yes, here's some. I didn't. These are all embedded processor manufacturers. And more than this, Atmel got bought by Microchip, Freescale got bought by NXP. So the world shuffles around. So a microprocessor is a very large-scale integrated circuit that contains a central processor and control circuits to move data in and out of the chip. A microcomputer is a desktop or laptop computer that uses a microprocessor, or a microcomputer if you want, and a number of supporting chips to provide memory, I/O, disk storage, displays, mouse, keyboard, and the whole 9 yards. So microcontroller is a chip that has most of the support on the same chip as the CPU, and it's used for a dedicated application. Usually there's not a keyboard, a mouse, and a screen associated with a microcontroller in an embedded design. Usually there may be a little user interface, but it could be on a 2x16 display with maybe a couple of push buttons and maybe a knob to turn. It can be fairly small. So in the last 25, 30 years, ARM has come along and just begun to dominate. And we're now at the point where essentially everybody manufacturing microcomputers has only a few companies still make their own cores. Microchip's one of the few left doing that. Most of the other companies have switched to ARM cores. Microchip does use some ARM cores for some of its chips, but their SAMD line and some other lines use ARM cores. The KO25Z is an ARM M0+. The ARM has A, R, and M chips typically, and the A are the high end, and the R are more for real-time things, and the M are for mobile applications. That's kind of how it works out. And what we're seeing is some of the ARM chips now beginning to push hard against Intel and AMD to take over the PC world. So this is going to be an interesting transition to see what happens. But the ARM cores are very, very powerful, and they're rivaling the Intel and AMD chips maybe at this point. I don't know exactly where the competition is, but they're getting some definite pressure, and we may see because the ARM chips are really powerful cores, and because they use a little more efficient language, they may win in the end. The Intel and AMD chips are still wedded to this very old legacy IA32 instruction set. All right. And here's some of the, Usually the way these companies do, like Freescale or now, let's see, where was that? I already forgot. Or NXP. So Freescale or NXP, what they basically do is they lease the ARM Verilog files, and then they get technical support to marry those files up with some of the old Freescale peripherals, some new and improved peripherals, all to make the KL25Z chip. And that's how it works. The ARM company itself has never, used to never make any silicon at all. I don't know if they make some now or not, but they used to make no silicon. All they did were write Verilog files, hardware description language files. Well, Verilog and VHDL files. But that may be changing. They may make some of their own silicon now. I'm not sure. Okay. So let's see. So so we're at 56 minutes. I'll go for about another 10 minutes. I'm going to talk about the programmer's model, and I'm going to compare it. I should, maybe what I'll do. I typically would compare it to the KL25Z, but actually, now that I think about it, I'd rather compare it to the Atmel ATmega 328. So I'll do that. So, but I'll make some comments here, and then I'll go back and talk about the Atmel 328 on Tuesday. All right. So here's the PIC, the 16F 1829. There is also an LF package. The LF package is a low voltage package. It only runs up to 3.3 volts, I think, or maybe it's 3.5, but it doesn't run all the way up to 5 volts. So we don't use this because we do like to have the ability to run it at 5 volts, because a lot of things we want to interface to are still in the 5 volt world. But a trend in microprocessors is that operating voltages go down, down, down. All right. So this only has 20 pins. Our KL25Z, on the other hand, has 80 pins. So it is a lot more complicated. It's a lot bigger. It's physically not a lot bigger chip, but it is. In terms of pins, it's got a lot more pins, and it's got a lot more functionality. But I think the feature size on the PIC chip is about 160 nanometers, and feature size on that is probably somewhere in the 60 or 48 nanometer range or something like that. Okay, the PIC is an 8-bit processor with 49 instructions, and it uses Harvard architecture. It has 1,000 bytes of RAM, 1,024 bytes of RAM, and it has 8 times 1024 bytes of program flash, and the program flash is 14 bits wide. So it's actually each instruction always takes 14 bits. And then it has 256 bytes of this non-volatile electrical erasable electrical programmable read-only memory. Now, Flash is EEPROM, but it's a little bit different. You have to erase multiple locations at once. Sometimes just a handful. Sometimes thousands. So it's a little bit different character, but it is still EEPROM. But we normally call Flash, and all the rest of the electrically programmable, electrically erasable read-only memories are called EEPROMs. Whereas on the KL25Z, it is a 32-bit processor. It has 56 instructions compared to, say, 49. All the instructions on this are 16-bit, except there's 6 32-bit instructions. It's von Neumann architecture. Now, what's the difference between von Neumann and Harvard? Well, Harvard architecture has completely separate address buses, data buses, and memory for programs and for data. In the case of the PIC, we have a 14-bit wide program memory that's all flash. And then on the data side, which has a 15-bit address line and an 8-bit data line. On the other side, we have a 12-bit address line for the special function registers and the memory, and we have an 8-bit data line for the data to flow on. So the nice thing about the Harvard architecture is you have a separate, you have extra bus. You have a bus to get your instructions, and you have a bus to move your data around and to get to your special function registers. Because of that, there is maybe a little bit of efficiency savings there. Whereas in the KL25Z, everything is in the same address space. Everything is in the same 4 gigabyte address space, and it has 16 kilobytes of static RAM and 128 kilobytes of programmable flash. And it doesn't have any EEPROM. All right, so on the PIC, you can normally just read the data sheet, and you can, with a little work and a little help, you can get going without too much trouble. KL25Z is definitely more complicated. For starters, there's a data sheet by NXP that tells you about the peripheral stuff, and then there's another data sheet by ARM that tells you about how the CPU and core stuff works. All right, so here is the, I'm going to skip over this. I might come back later and talk about it. So here is here's the programmer's model for the PIC 16F1829. It has these registers. Now, of these registers, I'm not going to make a big deal about the file select register 0 and 1 and the file select register 0 high, file select register 0 low, and file select register 1 high and file select register 1 low. So these are some registers. When you take the two registers together, we call them the file select registers. But because it's an 8-bit machine, we can only move 8 bits around at a time. We have to load them up 8 bits at a time. So we have an 8-bit file select register 0 and high, and a file select register 1 high, and also low for both. And the two taken together give you a 16-bit file select register 0. And these two taken together give you a 16-bit file select register 1. But we normally, So, okay. So we're not going to deal with these. These are used for indirect addressing for the most part. They have some real advantages, and obviously you should learn how to use them if you ever really work with this chip. But if you just use this chip for a little getaway and to see if it's going to work, yeah, you can do that with these registers without using these registers at all. When you program in C always uses these registers. Everything is done with indirect addressing. All right, and then finally, up here we have one working register. Now, if you compare this to the KL25Z, it has 13 working registers. So it's just got a lot more. But in this chip, we have one working register. In the KL25Z, they're all 32 bits, but in this one, the one working register is 8 bits. And then we have a bank select register, which only has 5 working bits in it. The other 3 bits are ignored, not implemented. And then we have a 15-bit program counter. And the upper byte is only a 7-bit byte, and then the lower byte is 8 bits. The lower byte is directly readable and writable, called the program counter low. But the upper 7 bits, we can't really write it directly. What we do is we load the 7 bits in the program counter latch high, and then when we write the program counter low, it automatically transfers what was pre-stored in the latch to the upper 7 bits. So you effectively do a 15-bit write all at once. This is necessary because the program counter goes out and gets the next instruction to execute. And if we wrote the 8 bits and then we came back and tried to write on the next instruction cycle the upper bits, it would be too late. We've already jumped to whatever the old value was up here with the new value down here, and that would have been a real mess. So because we preload the latch, when you do write the PCL low, you're writing all 15 bits at once. So the next fetch, the next instruction fetch then comes from the right place. So that works out. Okay. And then finally down here, then we have a program counter. Yeah, we just talked about it. Then down here we have the status register. And we have a Z bit, an H bit, and a C bit. We're going to ignore these other bits for now. The Z bit is set to a 1 whenever we do an operation with a register that winds up all zeros. So all 8 bits are zeros. When we're doing a mathematical operation, we overflow from the lower 4 bits to the upper 4 bits, like with an add, or we borrow from the upper 4 bits from the lower 4 bits or whatever with a carry, or then that bit will be set. And that was created to help with 2's complement math. And then we have a carry bit here. The carry bit is set whenever we overflow on a mathematical operation. So if we add 2 registers and we get a value that's more than 255, then the carry bit will be set, because 255 is the biggest number we can fit in 8 bits. And that extra bit then just goes in the carry register, and we can use it or ignore it depending on what we're doing. Okay, so that's the programmer's model. So a 8-bit working register called the W register, a 5-bit bank select register, and these 5 bits are used to finish the file register address. So when we address memory, we have to use this bank select register, and when we address most of the special function registers, we have to use this bank select register as well. There are 12 registers that are mapped to every bank, and there's 12 random access there's 16 random access memory locations that are mapped to every bank where we don't have to use this BSR. So you'll learn a lot about the BSR. We have to use the BSR a lot when we do assembly language programming. And then if we want to do a mathematical operation and then check for 0 or check for a carry, we can kind of ignore the half carry unless we're doing 2's complement math. So if you forget these, you don't have to know these. So these are the only ones you have to know. W register, the BSR, the program counter low, and the program counter latch high, making up the program counter, and the status register. So 1, 2, essentially 3, 4, 5 registers. That's it. That's your programmer's model. Okay, here's a block diagram of the chip. Here's the CPU with the programmer's model in it. Here is your program memory. It's all flash, and it's non-volatile, and that's what you flash when you download your program from the integrated development environment. So that program, once you download it, will always stay in your chip until you download something else and overwrite it. And so that's nice. If the chip powers down, when it powers back up, it'll resume execution at the beginning of the program, or it'll restart execution at the beginning. We have a built-in clock module, which can use external crystals, external RC oscillators, just a standard external oscillator, or it can do all internal clock generation. And it can go up to 32 megahertz. It has quite a few different timer selections, so you can change the clock frequency over a fairly wide range. And there is an internal RC oscillator that also is part of this. This is a fairly sophisticated clock module, but it's not nearly as sophisticated as, say, the KL25Z clock module. And then we have all these peripheral devices. Now, the ones up here are our random access memory and our EEPROM. And then we have port A, port B, and port C. So port A has 6 pins we can use. But we don't use 3 of them because they're involved in our debug interface. Port B has only 4 pins that we can use. One of them is tied up as the push button, RB7. But we don't have to use the push button, and so we could just ignore the push button and still use it. And then we have 3 other pins in that port. Port C has all 8 bits implemented. So we have 8 bits in port C, 4 bits in port B, and essentially of the 6 bits available in port A, 3 of them are not available because one is reset, and the other are the programming, the debug clock line and the debug data line. So that's how the integrated development environment talks to the chip. All right, and here are all the modules. So we have comparators, timers, analog to digital converter, digital and analog converter. It's not shown. SR latch, enhanced capture and compare, compare, and PWM ports. Got 4 of those, and then serial ports and I2C ports, and then a UART. So that's what we got. So the program's all here in flash memory. The data is all in data RAM. You could use the EEPROM for some non-volatile data storage, so that if you wanted to save data and power it down and power it back up and still have the data present, you have to write it into EEPROM, or it has to be part of the original FlashDIMM program. Here are our GPIO ports, are other pins that are used for the modules to talk externally to the chip. And these functions on these ports can be repurposed to do various different things. And finally, then we have all the peripheral modules, functional modules, and our clock generator. All right. So here's the core. I'm not going to go over this, but it's good to look at this. You'll see this in. This looks like a page out of your of course, Dr. Lin teaches how the CPU works, basically, but I've forgotten it. Flash program memory. This is our internal oscillator module. Here's our random access memory. So same parts here, and then this is the internal stuff on the CPU. There's the W register. Here's the BSR register. We'll go over this later. You'll see how the address is used. We take 7 bits from the instruction plus 5 bits in the BSR, and that gives us our 12-bit address for random access memory. Or we can get it directly from our indirect registers. Okay, here's our instructed register, where when we load an instruction from our flash program memory, it goes into here where it's decoded and executed. And the program counter is incremented and will fetch the next instruction. And here we have, if we jump to a function or a subroutine in assembler or an interrupt, we push the return address onto the 16-level stack and decrement our little teeny stack pointer. And that's what's if we nest things more than 16 levels deep, we'll be back to the top or overwrite our first return address, and we'll never get back to where we came from. And then here's the W register. And this is the arithmetic logic unit. Here's the status register. It gets its inputs off the ALU for zeros and carries and half carries. All right, I'm not going to go through this right now. We'll come back to this. This is just a reiteration of what we saw. These are the ones I want you to know. Program counter low, program counter latch high, status, BSR, W register. 1, 2, 3, 4, 5 registers to memorize for the programmer's model. You don't have to know the FSR 0 low and high and the FSR 1 low and high. You don't have to know the program counter. You don't have to know the interrupt control register. We're going to use it. And then these INDF0 and INDF1, these actually are not registers. They just refer to these 2 bytes for INDF0 or these 2 bytes for INDF1 when you actually write the instruction. But they're not actual locations. They just reference these actual locations. Okay. So again, the program counter is 15 bits. And when you write the program counter low, you have to have pre-written the latch high, and it puts 7 bits from the latch high and 8 bits from the low all into the program counter at one time, so you get a full 15-bit write, which is kind of tricky because remember, it's an 8-bit processor, so normally you can't move 8 bits around. So that's why you have to preload this latch, which is sitting right next to the program counter, and then it just dumps it in on a separate 7-bit data line. So we could have up to 32K of program memory, 14-bit program memory, but our chip doesn't have that much. Our chip only has 8K. Okay, again, we have a hardware stack, 16 levels. It's not available really for us to use, and stuff from function calls and subroutine calls and interrupts is automatically pushed onto it. Just the return address. Okay, I think that's it. I think I'm going to stop. We're at an hour and 15 minutes on the dot. So I'm going to stop with that, and I will see you on Tuesday.